Hi, I'm Jerry from the Lazer Robotics, and today I'll be taking a deeper dive into the mechanics of PID and how to fine-tune them to make your FLL robot more successful and consistent. So, why do we need a PID? Usually, the main reason teams use PID algorithms is to enhance the standard drive command. Because of the little bit of backlash that the motors have, using the regular drive command is not accurate enough for FLL. What a PID does is a simple error correction to guide a current sensor input to its target position. For example, a PID used to keep the robot driving straight would take an input from the gyro sensor. As the robot is driving, the gyro will detect if the robot is off its current target value and correct that. Now that we've gone over the main uses of a PID, I'll go over the mechanics of how it works in a drive command. But the same logic can be applied to pretty much anything. If you already have a solid understanding of a PID controller, skip to this timestamp. This is what the PID equation looks like. It seems complex at first, but once you break it down, it becomes a few easy equations. These equations then easily translate into code. The target value is usually 0 for gyro, which should mean your robot is pointing forward. Next, these three variables, Kp, Ki, and Kd, are called your PID constants. These are manually adjusted, and I'll explain them later. To calculate your error, you want to take the current sensor input, which is the angle of the gyro, and subtract the target value from it, which is 0, but will be different in the case of a line follower or something else. Then to find your integral value, you take the previous error from the previous loop and add it to your current integral. This number will constantly be adding up. Then to find derivative, multiply your error by your last error. Finally, to get a correction value, take your error, integral, and derivative variables and multiply them by their corresponding constants. So error times Kp, integral times Ki, and derivative times Kd. If that doesn't make much sense, it will later once you actually go to code it. After creating a PID controller, the next step is to tune your Kp, Ki, and Kd constants. This is usually the most time-consuming step. To start finding the optimal constant values, start with turning off the Ki and Kd by setting them to 0. Just to start with the Kp. To adjust the Kp, start with a relatively small number, such as 0.5. If the correction seems to not be doing anything, this value needs to go up. If it's very sharp and not smoothly correcting, it may need to go down. You can test your correction by when it's driving poking it and see if it fixes its path. You'll know when to stop changing it when it corrects as smoothly as possible to your given target. The next variable to tune is the Kd variable. In most cases, this should be less than the Kp value. Start with something around 0.25, and if it turns up, turn it up if you want to be more sensitive to sharp, intense outliers, and turn it down if it starts getting too sensitive. You'll know when it needs to stop when it corrects at a speeds that suit your need. The last variable, Ki, is a very, very small number. Start with 0.0001 and see what it does. Usually, the Ki value is not necessary for excellent navigation, but is nice to have. Now that we have established how to adjust the PID parameters, here's how we fine-tune them to suit our very specific needs. We use it for both gyro driving and line following, but we discovered that it works the best for line following. Starting with gyro driving, if the robot is pulling something on its side, more friction and drag is applied to that side. We would usually turn up the Kd value to compensate for all the friction. Now the line following. There are several situations where having a specific set of parameters is useful. One of them is line following around bends and circles. It can also help with turns and lines. This has been particularly useful in the past several seasons, especially in the Cargo Connect season and the current Masterpiece season. If you try to use a basic line follower built to move on a straight line to navigate around a curve, what will most likely happen is that it will see that there is an intense increase in white or black value and try to correct it, but it will not correct quickly enough to be able to stay on the line. The way we get away from it is to turn up the Kd value a lot. This was one of the weird situations where the Kd value is sometimes greater than the Kp value. We also found that turning the Kp value up or down can help, but this requires more extensive testing. And one more helpful tip for line following around bends is to slow down. Slowing down gives the robot more time to correct and adjust itself. This kind of complex FLL navigation is a lot to digest. It took us nearly 4 years to figure out and become comfortable with changing the parameters to suit our needs better. Of course, you don't have to start at this point. Many successful teams get away with using basic navigation tactics to move around. I hope this video helps better explain how to tune PID parameters and adjust them for certain situations. If you have any questions or problems while coding, feel free to leave a comment. Thanks for watching.